Okay, now this brings us to the first of two sections on two-dimensional NMR. And in a way, all of the things that we've done so far have been a preparation for being able to understand how these very important two-dimensional experiments work. So we'll use the product operator method extensively and all the ideas that come from that. So two-dimensional NMR has been around quite a long while now, and it has made a huge impact on the kinds of systems that can be studied by NMR. It makes it possible to study larger systems. It just makes those studies easier. And of course, as you know, it's also made accessible much larger molecules like small proteins and so on, which would have been inconceivable in the early days of NMR. And if you are working in a chemistry environment, things like COSY, HMQC, HMBC, I mean, these are utterly routine as far as the chemist is concerned. They would expect to be able to run these kinds of spectra on a day-to-day basis. Now, although we're not going to specifically talk about biomolecular NMR, the ideas that are contained within these two sections about the basic 2D experiments are absolutely transferable to biomolecular NMR. And all the stuff that they do with higher dimensions, 3 and 4 dimensions, it really is based very much on working out the same ideas. So although we're not going to address that specifically, the ideas in these two talks really do underlie biomolecular NMR. But we're going to concentrate on the basic experiments, COSY, HMQC, HMBC, things like that. And we're going to stick to two coupled spins because we can explain just about all of the key features using just a simple spin system like that. Now, the idea of two-dimensional NMR is pretty straightforward. In a conventional NMR spectrum, you plot intensity or amplitude as a function of frequency, and every peak has an amplitude and a single frequency. And in a two-dimensional spectrum, each peak has two frequency coordinates, and traditionally these are called F1 and F2. I'm going to call them omega 1 and omega 2 because it's usually easier for us to deal in radians. And usually these things are plotted as contour plots, so you have to imagine in that plot B that the peak is coming out towards you and there are contours on it as you would find on a topographic map. So each peak has two frequency coordinates as well as an amplitude. And the crucial thing in two-dimensional NMR is what do these two frequency coordinates tell you? And in almost all the experiments we're going to look at, these two frequency coordinates show you the correlation between two quantities. For example, they would show you that a spin with one chemical shift, one offset, is coupled to the other one with the other offset, and things like that. So it's this correlation of quantities which is the crucial thing in two-dimensional NMR. Now, you can describe almost all two-dimensional experiments using a single framework, and we'll do that. And that is the pulse sequence, which is shown in very general terms here. So you start out with what's called a preparation period, and this is basically some pulses. It may just be as simple as a single pulse, or it may be something much more complicated. And these pulses generate some kind of coherence which is going to evolve during the following period. And this may be just a straightforward magnetization on one spin. It may be something more complicated. You then have the evolution period, and this is the evolution period for a variable time T1. So T1 is a running time that changes from experiment to experiment. And you allow whatever coherence you've generated during the preparation period to evolve during T1. The important point to grasp is that you don't make any observations during T1. So for example, that means that you could allow a multiple quantum coherence to evolve during T1 because the fact that you can't observe it doesn't matter because you make no observations during T1. Then at the end of that you have a mixing period, and this is the crucial thing. This is the thing that causes the magnetization, for example, to be moved from one spin to another, that moves the multiple quantum coherence into an observable coherence. All the things that actually create the interesting features, the correlation features in a 2D spectrum, are the result of the mixing period. Now the mixing period may be, again, as simple as a single pulse, or it may be something altogether more complex. And finally, when you've done all of that, you have the normal detection period. This is the second running time, T2. And during this time, you really do record the signal, so it has to be an observable signal that you record as a free induction decay in the usual way. So what happens when you actually record a 2D experiment is you have to repeat the experiment for every single value of the time t1. So you start out with a time t1 set to 0, and that means that the preparation and mixing periods are right on top of one another, and you record the free induction decay as a function of t2, and of course that's digitized by the computer. I've shown it here as points, and that's stored away in the computer. And that's your first experiment. Then you do the first t1 increment, as it's called. You increment the value of t1 by a fixed amount, delta 1 here. You go through the whole experiment, record the data, store it away in the computer. And then you do it again for the second increment, which is 2 delta 1, and the third increment, which is 3 delta 1. So every single value of t1 requires a separate experiment. And this is why recording two-dimensional spectra can become quite a lengthy process. And it's also why you need to be very careful about how many increments of the time t1 you record, because the more you decide to record, the longer and longer it's going to take. Typically you might record between 100 and 1,000 different values of this increment t1. Now when you've done that, what you end up with in the computer is a matrix of time domain points. Right? Everything is measured as a function of time, so it's the time domain. And it's a matrix because you've got rows, they correspond to fixed values of t1 and changing values of t2. So the first row corresponds to t1 equals 0, and then all the different values of t2. And the second row corresponds to t1 is equal to delta 1 and all the different values of t2, and the third row, and so on and so on. So each row corresponds to a different value of t1. Now to turn this time domain data into a spectrum, you have to Fourier transform it, and you won't be surprised to find you have to Fourier transform it twice in order to get a spectrum. So first of all, you Fourier transform along the rows, and that just basically means you take out one of the rows, you Fourier transform it in exactly the same way I described before, and you put that back into the matrix, and then that's a spectrum. So the rows go from being as a function of the time t2 to being a function of the frequency omega 2. So that generates us the first Fourier transform. And then you do the same thing, but this time you go down the columns. So you take the first column, and that's a function of t1. You Fourier transform that, and that gives you the spectrum, which is now a function of omega 1. You do it with the second column and the third column, and the result of those processes is you end up with a matrix which is a function of omega 1 in one dimension and omega 2 in the other. So when you type Fourier transform on a two-dimensional matrix, it first of all Fourier transforms along the rows, and then it Fourier transforms down the columns, and that gives you a spectrum. Now it might be helpful just to have a look at what this data might look like in a very simple case. So what I've shown here is a two-dimensional data set. So you can see there is a function of t1 and t2, so this is the time domain data set. And I've just made it a damped cosine wave in both dimensions. And to make it easier to understand, it's shown as kind of a perspective thing rather than as a contour plot. So at the top left-hand corner, that's T1 equals 0, T2 equals 0, where the signal is a maximum. And if you go along T2, for example, shown by the arrow 1, if you take a cross-section through the data there, you get a damped cosine wave. And if you take a cross-section shown by arrow 2, that's along T1, you also see a damped cosine wave. So in fact, any way you make cross-sections through this, you just see damped cosine waves. Now I do the Fourier transform with respect to T2. That's with respect to the horizontal axis here. So now you'll notice in B, it's been relabeled omega 2. So if I take a cross-section, for example, at the arrow 3, that's parallel to omega 2, and I've Fourier transformed in that direction now, so I don't see a cosine wave, I see a peak, because I've Fourier transformed it to give me a peak. But on the other hand, if I take a cross-section at arrow 4, which is now parallel to T1, it's still the decaying cosine function because I haven't Fourier transformed that dimension yet. And then finally, if I do the Fourier transform with respect to T1, so now if you see in C, the plot is labeled omega 2, omega 1, and if I take a cross-section at 5 or at 6, I see a peak, because I've now Fourier transformed in both dimensions. And notice what's happened when you go from A to C. A is the time domain function, which is oscillating in both dimensions, and C, that's been Fourier transformed and produced a nice peak, which I fiddled it so it's in the middle of the spectrum. So that's the kind of process that's going on when you Fourier transform on the spectrometer. Now, unfortunately, in two-dimensional NMR, one of the things we do need to worry about quite a lot is the actual shape of these lines. Now, you remember in one-dimensional NMR, we said when we Fourier transform something, you get an absorption mode in the real part and a dispersion mode in the imaginary part. Or at least if you don't get that, you can adjust the phase in order to get that absorption mode, which is the desirable line shape. In two-dimensional NMR, it's a little bit more complicated than this, so we just need to be a bit cautious about this. So in one dimension, I said, well, if you had a complex decaying function, e to the I omega t, if you Fourier transformed that, you got the absorption mode A, and then in the imaginary part, you got the dispersion mode D. Now in a two-dimensional NMR, the function that you get is a bit more complicated. So in the square bracket on the left, you've got the modulation as a function of the time t1. And then in the square bracket on the right, you've got the modulation as a function of the time t2. Now the one on the right is exactly the same as the one we've already had. The one on the left is not exponential. I've actually put it in as a cosine. And in fact, typically in two-dimensional NMR, you get this cosine or sine modulation rather than modulation as the form of an exponential. We'll see that when we actually do a calculation on a two-dimensional experiment. Now we've still got to Fourier transform with respect to both dimensions and see what we get. So let's do that. So here's the time domain function. And then we Fourier transform it along T2, and what you'll get here is this term here, this A plus ID. That's exactly the same thing that we had before. And these are the absorption and dispersion Lorentzians along the omega 2 dimension. So that's done the Fourier transform one way, and now we need to Fourier transform this bit. And to Fourier transform the function of T1, we need to use a slightly different variant on the Fourier transform, and it's called the cosine Fourier transform, and that's not surprising because it's adapted to transforming things which are functions like cosine rather than these complex functions. But the difference of this is it doesn't give you an absorption and a dispersion, it just gives you the absorption mode. So when you Fourier transform with respect to the T1, you just get this absorption term here, and then when you multiply all of this out, you'll see in the real part you get A1, A2. That's an absorption mode in the omega 1 dimension and an absorption mode in the omega 2 dimension. So we call that the double absorption line shape. And in the imaginary part you get a mixed line shape, which we certainly don't want. So it's the same story. You would manipulate things so that you get the required double absorption line shape. And the double absorption line shape looks like this. It's called double absorption because if you take a cross section parallel to either axis, you get the absorption mode line shape. So this is the basic desirable line shape that you'll get in two-dimensional NMR. Now when we do our calculations, unfortunately we will discover that sometimes, rather than the modulation being cosine as a function of T1, it will be sine as a function of T1, and that's what we show here. And in order to deal with this, you need to use a sine Fourier transform. Again, it's just another variant of the Fourier transform, and that will give you the absorption mode signal. And if you work through the same algebra, you'll find in the real part, you'll get this double absorption line shape. Now the technicalities of this we don't need to worry about too much, but you just need to be aware that the way you process the two-dimensional spectrum is a little more complicated. You have to decide what kind of transform you're going to do in order to get the line shape that you want. Whereas in a one-dimensional one simply does the normal Fourier transform and then phases the spectrum. There's a little bit of added complexity here in the two-dimensional case. So, setting all that to one side, let's have a look at our first two-dimensional experiment, and we're going to look at the two-dimensional COSY experiment. It's the original 2D experiment, and it's typically done on proton as the typical nucleus. And this is used by chemists all the time, and typically what they'll do is get some kind of plot like this. Both dimensions contain the normal proton spectrum, so if you look along either omega 1 or omega 2, you see the usual proton spectrum. And this spectrum has two features. It has diagonal peaks, which are shown here in grey, and these have the same frequency coordinates in each dimension. So the one on the top right has the shift of A in one dimension and the shift of A in the other dimension. And they're not particularly interesting. What are interesting are these things such as the cross peaks, and they're shown in blue. And for example, the cross peak indicated there just between A and B, this one here, this has got the shift of A in one dimension and the shift of B in the other dimension. And because of the way this experiment works, that means that A must be coupled to B. So just by looking at this spectrum, you can trace out which spins are coupled to which. And you will spot that A is coupled to B, and B is coupled to D, and C is coupled to E. But for example, there's no coupling between A and D. And of course the beauty of COSY is you can explain that to someone in 30 seconds, and they can then go away and assign a spectrum. I mean, that's absolutely perfect. You can see why these things have become so popular. But what we're going to do is look at why these cross peaks appear and what their features are. And in particular, we're going to look in some more detail at the fine structure of these peaks. I've just drawn them here as blobs. In fact, they've got a more detailed fine structure, which is quite interesting as well. So we're going to do a detailed analysis of COSY just for two coupled spins. The pulse sequence couldn't be simpler. It's 90 T1, 90 acquire. So the preparation period is just a 90-degree pulse. The mixing period is just another 90-degree pulse. And everything is about X unless you say otherwise. We're going to do this for two coupled spins, and I'm going to start out first of all with the equilibrium magnetization on spin 1. So I'm going to start with I1Z. So the first 90-degree pulse takes that to minus I1Y. And then during T1, two things are going to happen. The offset is going to evolve, and also the coupling is going to evolve. It's not a spin echo, so neither of those things are being refocused. So if the offset evolves, the Hamiltonian is omega 1 I1Z, and so you get an I1Y and an I1X term. And then you have to allow the coupling to evolve, and you have to take each of those terms and allow the coupling to evolve on them. So you have to take the I1Y term, and it's got this cosine omega 1 T1 factor in it, which is highlighted in red. And notice, as we've said before in these calculations, that just carries forward as a factor, and then you have to allow I1Y to evolve under the coupling to give you I1Y and 2I1X, I2Z. And then likewise you have to do the same thing with the I1X term, and again the term sine omega 1 T1 carries forward as a factor. So at the end of this, after you've allowed the coupling and the offset to act, you end up with 4 terms. So that's got us to the end of T1. And then what we need to do is to apply the final pulse in the sequence. Now remember that this is a homonuclear system, so the pulse is applied to spin 1 and spin 2. So what's written over the arrow there is a 90-degree pulse to I1X and I2X. And you'll see each of these terms does something different. The first term switches on to Z. The second term becomes multiple quantum, 2I1X, I2Y. And the third and the fourth terms are actually observable terms. So let's concentrate on the observable terms. Term 3 is observable on spin 1. I know that because it comes out as I1X. And it's modulated in T1 at the frequency omega 1, big omega 1. You can see that there because it says sine big omega 1 T1 in red. So this peak, this term, gives rise to a diagonal peak. And it's a diagonal peak because it appears on spin 1 in the omega 2 dimension, and it appears at frequency big omega 1, that's spin 1, in the little omega 1 dimension. So it has the same coordinates in each dimension. And therefore this term gives rise to a diagonal peak. Term 4, now highlighted in green, this gives rise to a different peak. So first of all, notice that it's observable on spin 2, because it's 2I1Z, I2Y. Of course, that is the result of coherence transfer, which is what the last step is. But it's modulated at sine omega 1 T1 in T1. So this appears on spin 2 in the omega 2 dimension, and at the offset of spin 1 in the omega 1 dimension. So term 4 is a cross peak. Right? So term 3, which results from no coherence transfer, is a diagonal peak, and term 4, which results from a coherence transfer step, is a cross peak. Now, I started out with the equilibrium magnetization on spin 1, I1Z. So what you now need to do is go back to the and redo the calculation, starting out with the equilibrium magnetization on spin 2, which is I2Z. The calculation is very easy because all you have to do is swap the indices 1 and 2, and you'll end up with 2 more terms, which I call 5 and 6 here. And if you look at these, you can see that term 5 is observable on spin 2, so it says I2X, and it's modulated at the frequency of spin 2 in the other dimension. It goes as sine omega 2 T1. So that's a diagonal peak at the coordinates of spin 2 in each dimension. And term 6, that's a cross peak It's observable on spin 1 because it's 2I1Y, I2Z. And it's modulated at the frequency of spin 2 in the other dimension. It goes as sine big omega 2. So that's a cross peak. Right? So in fact what we've got is 2 diagonal peaks and 2 cross peaks. So if we think about what the spectrum looks like in schematic terms, it's going to look like this. Look at the axes first. Little omega 2 is horizontal, little omega 1 is vertical. And for example, term 3, that is the diagonal peak which is modulated at the offset of spin 1 in the little omega 1 dimension and comes out on spin 1. So that's peak 3 in the bottom left-hand corner. And 5 is the other diagonal peak, and that appears in the top right-hand corner. Then you've got the 2 cross peaks, terms 4 and 6. So 4 is modulated at big omega 1 and comes out on spin 2. So that's on the bottom right-hand corner of the spectrum, and so on. So what we predict for this cozy spectrum is 2 diagonal peaks, which are just at the same shifts in both dimensions, and 2 cross peaks, which fill in these square-related dimensions. But I emphasize here that I'm still drawing these cross and diagonal peaks as blobs. I'm not actually showing the fine structure, which we'll come to in a moment. And of course, if the J coupling was 0, then these antiphase terms wouldn't be created, and there'd be no coherence transfer, and the coupling and the cross peaks would disappear. You can see that because if you look at the cross peak terms, they go as sine pi jt. If j is 0, that sine term is 0, and those cross peaks will disappear. So you only see a cross peak if there's a coupling. So that's the whole utility of this cozy experiment.